cellular or even subcellular scale, especially for some of the animal studies that we'll do in preparation. So here's an example of huge incremental changes. So, holding it back, DNA is a detector, so the DNA is a detector for exotic particles in the universe. DNA is a detector for crowd. Try to get some basic information out of the computer and into DNA. Then the next step is DNA delivery on the next slide, and then the third slide will be once the DNA is delivered to the roughly right place, of splicing it into the genome perfectly, not just putting it in some extra random place. So the cheapest we can do for raw DNA synthesis is on the order of 1 to 200 base pairs, millions of those things on a chip, made similar to chips in your phone, on the order of hundreds of dollars per chip. So you make 600 million base pairs on a chip for hundreds of dollars. But then you have to do steps 2 or 3. You have to deliver the DNA. We can deliver single base changes scattered all over the genome, or we can deliver big chunks of DNA, up to 10 million base pairs, by either a process called CAGE or by microcell chromosome transfer. This is where we stand right now in terms of, and it's probably adequate, but will improve by factors of 10, just as sequencing and synthesis have. And the third step is splicing this in very precisely. In 1990, the first human trials on gene therapy were approved by the FDA. They were not precise. They approved putting in random pieces of DNA that added to your genome to fix rare genetic disorders that had the unfortunate consequence of causing cancer to some people and so were short-lived. 6 years later, introduced the first really amazing way of doing targeted change, which was the zinc finger nucleases, and these have dominated for the 17 years since. But the new actors appeared in the field. My group and others have introduced this CRISPR technology, and I could spend an entire hour or two on this, but just 1 second. It's now not just protein-guided with the 3 fingers of the zinc finger illustrated, but it's RNA-guided nuclease. The nuclease cuts the DNA, and then you can either just get rid of the DNA or introduce something new. So those are the 3 ways that we see changing rapidly in a very positive way for human gene therapy. Now, here's an application. How does HIV get into humans, and what can we do about it? It gets into humans via the CCR5 gene, which is present on all of our T cells, almost all of our T cells, and it gets in, and it causes one of the greatest epidemics in human history, and extremely sad. And many of these are drug-resistant and vaccine-resistant. Here's those fingers again. Now, not 3 fingers, but 8 fingers, binding and a nucleus in the middle. This is a hybrid molecule. It's a hybrid between a mammalian set of zinc fingers and a bacterial nuclease, and it's going in and it's making a hybrid genome. You can go into patients, take out the T cells, to make both copies of their mother's and father's copy of the CCR5 gene, put them back into the AIDS patient. The AIDS patient is cured and is resistant to future AIDS infection, HIV. So this is an example of the kind of motivation for developing this technology, which will have spin-offs in exactly the fields we're talking about here today. This is an example of that surface of that cell where the AIDS virus is binding, and this is one of the first patients in a previous study, but this is now inspired and expanded to a full phase 1 and now phase 2 clinical trial of the company Sangamo, which makes using finger nucleases to cleave and alter both copies of the CCR5 gene. So this is real, not science fiction, and is potentially applicable to endangered and extinct species. I think it's important to lump these together, the endangered and the extinct, and habitat preservation. All of these, synthetic biology has hopefully something good to say and to contribute if we all behave responsibly and as we are now. The Tasmanian devil has got the opposite problem of humans. It has too little immune diversity. And so there's actually transmissible cancer that they kind of bite each other when they're fighting. And normally that would just cause a few cuts, but this now transmits a cancer. It's actually a Tasmanian devil cells go from one to another. And we heard earlier talk that we want Tasmanian devil to develop a free methylbiocene. So you might be able to get a little diversity from existing Tasmanian devils, or you could go back and get from information that we can get from extinct dead versus these and introduce that diversity. So, as I said, humans have the opposite problem. They have too much immune diversity, at least too much from the standpoint of transplantation. If you want to get an organ donor, you have to search the world over to find somebody, and even then, the lines are very long, and it's very unfortunate. So we can increase or decrease diversity by looking at this little set of genes on chromosome 6 of humans, and there's a corresponding chromosome in Tasmanian devils and all of the animals we're talking about here today. You can go in and change as little as 2 to 5 of these genes to increase the diversity of the Tasmanian devil, or a few more genes, and you can make the tissue that you want to transplant, the stem cells you want to turn into organs to transplant, compatible with just about any human without having to find a specific donor. Small number of genes can make amazing differences in both of these 2 species. Sergei Simov has been telling us at least since 2005 of the potential impending threat to the entire world that comes from the threat to the Arctic carbon. There's more carbon sequestered in the grasses and other things in the Arctic than all the rainforests burnt to the ground. I don't recommend this, but it's hypothetical. Times 2.5. So, and it's not just, it doesn't require burning the carbon, it just requires melting it. This is currently happening. You can see some of the slides of speakers. So, this is hypothetically a solution to this, but we need to explore whether this is the only solution or the more adequate one. Getting rid of the dead grass, swamping down the trees, and swamping down the insulating snow in the winter so that Arctic trees can get into the permafrost. These are the sort of things that could be achieved uniquely by mammoths. And so Sergei Simov and his colleagues have created Pleistocene Park that's currently populated by much smaller mammoths. We would propose to make a hybrid elephant that has the best features of modern elephants and the best features of mammoths. We have enough of a mammoth genome and enough information in computers about many other species to know the key physiological features that we need to introduce in the elephants so that they will be happy year-round in the Arctic regions of Canada and Russia. Many of these have actually, maybe to some people's surprise, have already been recreated. 5 different gene variants have been tested either molecularly or in cells, including blood hemoglobin and genes involved in hair color. And we want to get at other ones even more vital to the cold, having to do with subcutaneous fat. And sebaceous glands and sebaceous elements don't have a short, stubby, bristly hair that causes cooling rather than the insulation that we actually want. Developmental biology is currently one of the big pushes forward for synthetic biology, and it's going quite well. Spectacular results already, and we're just starting. Here's an example of a mouse incisor, which has 3 changes in the genes, and the spy genes can become very tusk-like. In the lower example, where you have 3 mutations from the CSF. You can learn from many animals, not just from the mammoth DNA, but from developmental biology in many animals, including humans. Here are 2 human mutants that cover this huge range of hair, ranging from very sparse hair, kind of like what you see in the elephant, tail and legs on the left hand. But we have various tools, you've seen some already, not just my talk and others, where we can test a few genes at a time in molecularly, cellularly, or in increasingly in organs and systems. Again, being developed for human health. We want to be able to develop organs in the lab so that we can use it for transplantation. And you can test out whether what you think is going to create the subcutaneous fat layer or the woolly hair is there. And these are examples of tests from stem cells, actually from my own body, in the case of the ones on the right, where you can generate almost every tissue in the laboratory, either in mice or in tissue culture. So, again, what's important is for this community to come together and hear your voices of practicality and pragmatism and what you want to see done and how. Thank you very much. Duplicating cells is really like duplicating a small city. Lots of things have to happen. And there's a blueprint that describes and controls this entire process. This is the DNA. You can imagine that this blueprint is copied painstakingly because it's so important to get it right. But it cannot be perfectly copied every time. We discovered an important aspect of something we now call the DNA damage response. And it's a signaling network to inform the cell that there has been a problem with DNA replication. So DNA damage is treated as information. And the cell responds to that information and orchestrates repair. The DNA damage response pathway is critical for human health. For example, if you interfere with it in any way, you get genomic instability, which can lead to cancer. And if people are born with relatively subtle mutations in this pathway, not completely destroying it, they have very severe developmental defects. So I'm George Church, professor of genetics at Harvard Medical School, investigator of the Peace Institute for Biologically Inspired Engineering. We work on advanced technologies for reading and writing in DNA and neuronal systems, aging and so forth. We have many good things that we hope to tell you in June 2013, and really looking forward to seeing you there. So I'm really looking forward to seeing you at Global Futures 2045 in New York Lincoln Center in June 2013. Right now we back up. And it's a very cool, it's a very slow process, and it's a very poor copy. It's nothing like what we consider a good copy of a computer. Cloning of people even if it were done, which it isn't. prevent your brain from getting Alzheimer's is to figure out why some people never get Alzheimer's and inject those genes into your brain. But then there are other aging processes. We're getting much better at gene therapy. We now have 80 gene therapies in clinical trials. Some of those work on post-Maykai cells like muscles and nerves. If we get to the point where we can reprogram the neuronal cell body, then we can retain all the connections of the neurons that have built up over a lifetime of experiences, just rejuvenating the central process of the nucleus of the cell. And you can think of it in the same way that we're kind of updating.